Okay, everybody, we're here to do some geometry and we're starting chapter 12. Chapter 12 is all about circles, which is going to be exciting because you know how awesome I am at drawing circles on the board. So this is going to be amazing and I'm sure you're going to love it. So let's get started. 12.1, page 792. So I have the circle here already ready to go. It's beautiful. We're going to talk about the parts of a circle. The first one is a chord. A chord goes from one point on the circle to another point on the circle. That's called a chord. Okay? If the chord happens to go through the middle of the circle, it's a special kind of chord, and that's the diameter. Okay, so the diameter is technically a chord. It's just one that goes right through the middle. Okay, so the next one they want you to learn about is a secant. I know I'm totally mixing pin colors, but it's okay because the darker one is the one that's getting mixed. Then we won't even be able to tell. So it's okay. I know you're scared and worried, but it'll be all right. So a one that just goes shooting through the circle anywhere is called a secant. So that's the second one on that of the yellow words there on 792, a secant. Secant. There we go. Just kind of goes shooting through the circle. Okay. The next one in the box there on page 792 is what we call a tangent. A tangent goes running next to the circle and touches it at one point as it goes by. Okay? It just kind of touches up next to the circle at one point as it goes by. By the way, this right here is called the point of tangency because that's the point where the tangent touches the circle. So obviously that's the point of tangency. Okay? So those are the three segments they're talking about in circles for this section. So let's look at example number 1. If you had to list the chords, what would you say there for example number 1? This is going to confuse a few of you, but I think you'll get it after we talk about it. One chord would be BC, right? Or we could say CB. That's okay. Also, another chord would be from here to here. Even though that's also a secant, if I called it a line segment, if I only was talking about the distance from here to here, that would technically be a chord. So we could also say on our example 1 that EF is a chord, even though it's also a secant, right? It's just all about the labeling. If I said EF like this, it would be a chord. If I said EF like this, it would be a secant. So it's just all about labeling, okay? So just be very careful with your details. Okay, the radii, which is plural for radius, instead of saying radiuses, I guess, AC and AB. The secant is EF, we talked about that already, and the diameter is BC, has to go through the middle. Okay, so those are the parts of the circle. So let's look over at some more stuff about circles. Some of this is pretty logical, I think, for you, so hopefully it won't be too terribly difficult in this section. On page 793 in the box, congruent circles have the same length of a radius. So their radii are equal if they're congruent circles. Okay? Concentric circles are like the target symbol. Those have the same center. Their radii will be different, but the center of the circles will be the same, concentric. Okay, and the last one there is tangent circles. Tangent circles are circles that run into each other at one point only. Look at that circle, that's amazing. So this would be the point of tangency. You can also have tangent circles inside, like one could be inside, and that would be the point of tangency. Okay, so those are tangent circles. So let's look at example number 2. It says to identify the length of the radius in those circles, their point of tangency, and also an equation of a tangent line. So let's look at our picture. We can just count, because it's on a graph, the radius of circle A is, I'm just going to count, I see the middle there, and I'm going to count all the way over to the edge, and I see that that's 4. So I can say radius of circle A, radius of circle B, or whatever, probably not B. What is B? Circle B is, let me count there on my graph, I can see where the middle is, and it looks like it goes 2 over to get to the edge, so the radius of that guy is 2. The point of tangency is where let's see, my circles look like this. The point of tangency is where they run into each other, and we're looking for an ordered pair because it's on the graph. So where they run into each other looks like it's at over 3, up and down 0. So the point of tangency is over 3, up and down 0. Okay, and the last thing they want to know is the tangent line. Now, the tangent line is a line that goes through like this through the point of tangency, right? And is tangent to both circles. What kind of line is an up and down line? Is that an x equals something or a y equals something? Does anybody remember? Okay, it is an x equals something. So our tangent line is x equals, and what point does it go through right there? Looks like it goes through 3. So that would be my tangent line. Okay, so I've listed all the things they asked me for there. On check it out number 2 at the bottom of page 793, notice my line is going this way this time. So my tangent line is going to be a y equals something for that problem. Okay, let's look at the next page. Okay, if we have circles like they show us at the top of page 794, there might be a tangent that is common to both circles. Okay, both circles may have a tangent that in common. Okay, so there could be circles like this, and they have a tangent that goes like this, right? Like they show there. One's bigger and one's smaller, but the same kind of thing, okay? So a line that's tangent to both of them, let's say like this, okay? That would be a common tangent to both of them because it doesn't go through in between them. It's an external tangent, common external tangent, okay? On the other picture, it goes through in between both of them like that. That's a common internal tangent because it goes inside or crosses over like the middle of them, okay? Common external tangent, common internal tangent. Okay, external if it doesn't cross through the middle at all. Internal if it does. All right, let's look at the theorems on 794. If I have a circle and I have this radius here, and I have if the radius hits at the point of tangency, well, that's not going to work. If there's my point of tangency on this kind of smashed circle, sorry. There's my point of tangency. If the radius runs into the point of tangency, which it does here, that will create a 90-degree angle. And it works both ways. That's why there's 2 theorems there, okay? If you know that it's perpendicular, then you know that this is a line of tangency. So if you have a tangent and the radius hits at the point of tangency, it creates a 90-degree angle. All right. Now, let's look at, before we do example 3, let's look at the theorem on the bottom of page 795. Okay, if I have a circle, man, this pen is terrible, and I have a point out here, and I draw a tangent to this part of the circle and another tangent to this part of the, my example doesn't actually show that this is true. Let's try it again. To this part of the circle, the rule is if they come from the same point and they're tangent to the same circle, they're equal to each other. Okay, so if I knew that this was 4y and this was 12, I could say 4y I know is equal to 12, and that's how I could figure out what y is. If they come from the same point and they're tangent to the same circle, they're equal. Okay, now let's look at the example number 3. This is a kind of a confusing problem, and you'll have one like this in your homework as well. It has to do with the radius of the Earth or the distance around or something, which you might have to look up if I'm remembering correctly, or we could just use this here. We are going to talk about example number 3. So the picture that they draw for this example is super helpful. So I'm going to attempt to reconstruct that picture real quick here. Okay, I'm close. It's close. Okay, I'm going to make this a 90-degree triangle. So the summit of Mount Everest is approximately 29,000 feet above sea level. So if this is the Earth and this is the top of Mount Everest, this distance right here is 29,000 feet. Because This is the middle of the Earth, and Mount Everest, they're not talking about Mount Everest inside the Earth. They're talking about from the crust or the surface of the Earth to the top of Mount Everest is 29,000 feet. Then they told us that this distance right here, which is just like the radius of the Earth, I guess you could say, is 4,000. Okay, so wouldn't this distance here also be 4,000? Okay. This is in miles, by the way. That's why it's not really looking like it's drawn to scale. It's because the 4,000 is miles. Okay, so we now have a triangle where we know the parts, and the thing they want to know is what is the distance from the summit to the horizon? This distance right here. Okay, so hopefully that helps you set up the problem. Now we just have a right triangle and we can just do Pythagorean theorem. The only thing that we're going to run into is making sure we're dealing with miles in both places. So I have miles here and miles here, so why don't I change 29,000 into miles? So 29,000 feet divided by 5,280, they did that for us, is 5.49 miles. Okay, so instead of feet, I now have it in miles. So let's look at our right triangle. I'll draw it. Oh, yep, I'm drawing it the same way. Okay, so I know that this is 4,000. This is a mystery number I'm trying to figure out. And this is the 4,000 plus the 5.9, right? The 4,000 from here to here plus the 5.9 from here to here. So 4,005.49, I meant to say 0.49, sorry, is what the hypotenuse is. We can do the Pythagorean theorem, and it looks like we'll get 210. So our answer is 210 miles. Okay, so when you're doing this in your assignment, which is going to be number 8 and number 15, just make sure you draw the same little picture that we used for Mount Everest, but you can know that the radius of the Earth, which you're going to use again, just use 4,000 for that. Okay? All right. I think that's all we need to know. Example number 4, I kind of already showed you how to do that. On example number 4, they're coming from a common point and they're tangent to the circle. So 5y minus 28 is equal to 3y. Okay? So lastly, of course, because I know you only watch these videos for the joke. Oh, wow, this is going to be crazy because I have to actually show you this one. Okay, well, I apologize for this. Here we go. Let's give it a try here. Let me rotate you around. I can't rotate you around. Oh, boy. Okay. Nope, wrong way. Why can't I flip the camera? That doesn't make any sense whatsoever, people. No sense whatsoever. Okay, there it is. I finally got it. What is the hidden math term? You see that little crayon dude? Hopefully he's in focus. I don't know. The hidden math term. Ready? A tangent